In this lecture, we find out the radius of the circle using two different methods. In the drawing, we have triangle ABC, and this triangle ABC blocks the circle, or the circle is inscribed by triangle ABC. In addition, we know that this angle ABC equals to 60 degrees in its size. This is angle ACB that equals to 75 degrees in its size. And we also know that side BC of triangle ABC equals to 2 units in its length. Our mission is to find out the radius of this circle that is inscribed by triangle ABC. So we'll start with the first method. And in the first method, we will do a construction. That is to say, from point C, we'll draw a perpendicular on side AB. Okay. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C on AB as D. And we'll focus on the right triangle DBC. So I'll copy the right triangle DBC in a new page. So actually, this is the right triangle DBC that I copied from the original drawing. In this right triangle DBC, cosine 60 degrees will be equal to dB over DC. So I write it down. Cosine 60 degrees equals to dB over DC. dB over BC. The hypotenuse is BC. So it is dB over BC. BC equals to 2 units in its length according to what is given us the question. So if we're going to find out that cosine 60 degrees equals to dB over 2. Cosine 60 degrees equals to 1/2. So we substitute cosine 60 degrees by 1/2. This equals to dB over 2. dB over 2. Here we multiply this equation by 2 and finally we get that dB equals to 1 unit in its length. dB equals to 1 unit. So we can write down in the original drawing that side dB equals to 1 unit in its length. We continue to focus on the right triangle DBC. On the right triangle DBC, sine of 60 degrees equals to DC over BC. DC over BC. So sine of 60 degrees equals to DC, that is the missing side, over BC. BC equals to 2 units in its length according to what is given as the question. So BC is 2. Sinus 60 degrees is equal to 3 over 2. And square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2 and finally we will get that DC equals to the square root of 3 units in its length. So here this side DC equals to the square root of 3 units in its length. Here we know that the sum of the angles in any triangle is equals to 180 degrees. It is also true in the right triangle DBC. So this angle equals to 90 degrees, this angle equals to 60 degrees, therefore the missing angle must be equal to 30 degrees. The missing angle here must be equal to 30 degrees. We know that angle ACB equals to 75 degrees. So 75 degrees minus 30 degrees equals to this missing angle. So the missing angle, angle ACD, equals to 75 degrees minus 30 degrees, it is 45 degrees. In the next step, we'll focus on the right triangle, triangle ACD. So I'll copy the right triangle ACD in a new page and we'll analyze it. So actually, this is the right triangle ADC that I copied from the original drawing. We just right now found out that DC, side DC on this right triangle ADC equals to square root of 3 units in its length. So this angle is 35 degrees, this angle is 90 degrees. Therefore, the missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. And we have the rule that in front of equal angles in a triangle there are equal sides. So in front of those two equal angles, we have those two equal sides. That is to say, side DC equals to side AD. But DC equals to the square root of 3 units, therefore AD must be also equal to square root of 3 units in its length. So here, side AD equals to the square root of 3 units in its length. We continue to focus on the right triangle, triangle ADC. Here, in the right triangle, triangle ADC, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in the right triangle, triangle ADC, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. Again, according to the Pythagoras theorem, in the right triangle ADC, AC squared equals to AD squared plus DC squared. So AC squared equals to AD squared. AD is equal to 3, therefore AD squared is equal to 3 squared, that is 3, plus DC squared. DC is also equal to 3, therefore DC squared is equal to 3 squared, that is 3. So AC squared equals to 3 plus 3, that is 6. AC squared equals to 6. we take a root out of this equation and finally we get that AC equals to the square root of 6 units. So this side AC of the triangle ABC equals to the square root of 6 units in its length. In the next step, I present to you a new rule, and we'll implement the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is inscribed by a triangle ABC that could be any triangle, the radius R equals to the area of triangle ABC that blocks the circle over S. S is the semi-perimeter of triangle ABC that blocks the circle. Okay. So here we have, this is triangle ABC that could be any triangle. Triangle ABC blocks this circle, or this circle is inscribed by triangle ABC. So actually we can know what is the radius of this circle only by knowing the area of triangle ABC that blocks the circle and the semi-perimeter of the triangle. So the radius of this circle that is inscribed by triangle ABC equals to the area of triangle ABC over the semi-perimeter of the triangle. The semi-perimeter of a triangle is the perimeter over 2. So the radius of this circle that is inscribed by triangle ABC equals to the area of triangle ABC over the semi-perimeter. And the semi-perimeter of triangle ABC that blocks the circle equals to the perimeter of the triangle over 2. The perimeter over 2, that is to say it is AB plus BC plus AC, that is the perimeter divided by 2. So we can actually implement rule number 15 in our drawing. Why? Because in our drawing the radius of this circle that is inscribed by triangle ABC, here the radius R, we define the radius of this circle as R. According to rule number 14, the radius R, then according to rule number 15, the radius R of this circle that is inscribed by triangle ABC will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC that blocks the circle. So the area of triangle ABC equals to the base of the triangle times the height to the base over 2. The base is AB times the height to the base. The height must create 90 degrees with the base. Here DC creates 90 degrees with the base, therefore this is the height. So it is AB, the base is AB, times DC, the height is DC, over 2, divided by semi-perimeter of triangle ABC. The semi-perimeter of triangle ABC equals to the perimeter over 2. The perimeter is AB plus BC plus AC, AB plus BC plus AC divided by 2. So here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. And finally we actually found out that the radius of the circle that is described by triangle ABC equals to AB times DC over AB plus BC plus AC. Okay, so we have already found out that AB equals to the square root of 3 plus 1 times DC. DC equals to the square root of 3 units over AB. AB is equal to 3 plus 1 plus BC. BC is 2 plus AC. AC is equal to 6. Okay? So here, the square root of 6 plus 1 square root of 6 plus 1 times square root of 3 equals to 2.366, that is to say the area of triangle ABC equals to 2.366 square units divided by the semi-perimeter of triangle ABC. This expression square root of 3 plus 1 plus 2 plus square root of 6 equals to 3.591, and 2.366 over 3.591 equals to 0.6589 units. In conclusion, we found out that the radius of this circle that is described by triangle ABC equals to 0.6589 units. Okay, that is the answer to the question. So we finished with the first method. In the next step, I will present to you how to find out the radius of this circle that is described by triangle ABC according to the second method. We define the center of this circle as O. We define the point of tendency of tangent BC with this circle as M. We join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of this circle that we define as R. The radius of this circle is the radius that we are looking for. According to rule number 1, a tangent to a circle is perpendicular to the radius 1 to its point of tendency. Again, a tangent to a circle is perpendicular to the radius 1 to its point of tendency. Here we have tangent AB, that is tangent to the circle at point M. Point M is the point of tendency. And according to rule number 1, whenever you have a radius that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle. Then tangent AB will be perpendicular to the radius MO. That is to say this angle equals to 90 degrees and this angle equals to 90 degrees according to this rule number 1. So according to rule number 1, we have the radius OM that is 1 to point M, that is the point of tendency of tangent BC with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius OM. If BC is perpendicular to OM, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. Okay, we define the point of tendency of tangent AB with this circle as D. The next step, we join points O and D together by a straight line. Point O is the center of the circle, point D is the point on the circle itself, therefore OD is the radius of this circle, that's equal to R. Again, the radius OD is drawn to point D, that is the point of tendency of tangent AB with this circle. Whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius DO. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. We define the point of tendency of tangent AC with this circle SE. We join points O and D together by a straight line. OE is the radius of this circle is equal to R. Again, we have the radius OE that is drawn to point A, that is the point of tendency of tangent AC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius EO. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. In the next step, we will present you according to rule number 2. We have here, we can implement here rule number 2. According to rule number 2, the lengths of two tangents from common standpoint to a circle are equal. Here we have the common standpoint point P. From the common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. According to this rule number 2, they are equal to each other. That is to say, PA equals to PB. We can actually implement rule number 2 in our drawing. Why? Because in our drawing, we have the common standpoint point C. From the common standpoint point C, we have two tangents to this circle, tangent CE and tangent CM. And according to rule number 2, they are equal to each other. That is to say, CE equals to CM according to rule number 2. Likewise, we focus on the common standpoint point B. From the common standpoint point B, we have two tangents to this circle, tangent BD and tangent BE. And according to rule number 2, they are equal to each other. That is to say, BD equals to BM. So I write it down. BD equals to BM according to rule number 2. In the next step, we will join points O and B together by a straight line. And we will prove that the yellow triangle EDO is congruent to the green triangle, triangle OBN. Okay, again, we prove that the yellow triangle, the yellow right triangle is congruent to the green right triangle. So I write it down. we prove that the green triangle DOB, the green right triangle DOB, and the yellow triangle DOB, this is the yellow triangle DOB, is congruent to the green triangle BOM. So why the yellow triangle is congruent to the green triangle? First of all, BD equals to BM according to rule number 2. BD equals to BM according to rule number 2. Okay. Repeat again. Side BD of the yellow triangle equals to side BM of the green triangle according to rule number 2. In addition, sides DO and OM, they are both the radii of this circle, therefore they are equal to each other. DO in the side DO in the yellow triangle equals to side OM in the green triangle. They are both the radii of the circle, therefore they are equal to each other. Repeat again. Side DO in the green triangle equals to side OM. Again, side DO in the yellow triangle equals to side OM in the green triangle. They are both the radii of the circle, therefore they are equal to each other. And finally, side BO is a common side that belongs to both triangles, so we can write down that side BO equals to itself as a common side that belongs to both triangles. So BO equals to itself. Repeat again. Side BO equals to itself as a common side that belongs to both triangles. So we actually prove that all the three sides of the green right triangle are correspondingly equal to all the three sides of the green triangle BOM. Therefore, we actually proved that the green right triangle DBO is congruent. This is a sign of congruent to the green right triangle BOM. According to side rule. Okay. And from the fact that those two right triangles can go into each other, we will derive that those two angles are equal to each other. So this is angle DBO in the yellow triangle. This is angle DBO in the yellow triangle. And it is equals to this angle. It is actually angle OBM in the green triangle. Repeat again. From the fact that the yellow triangle DOB is congruent to the green triangle BOM, we will derive that angle DBO in the yellow triangle equals to angle OBM in the green triangle. Okay. According to the rule that corresponding angles in congruent triangles are equal to each other. those two triangles can go into each other, therefore the two corresponding angles must be equal to each other. Those two corresponding angles must be equal to each other. So if we define one of those two angles as theta, then the other angle must be also equal to theta. Okay? Because they are equal to each other. Okay, so if this is angle theta, then the other angle must be also equal to theta because they are equal to each other. So theta plus theta equals to 60 degrees according to what is given us the question. That is to say 2 theta equals to 60 degrees. We divide this equation by 2 and finally we get that theta equals to 30 degrees in its size. So actually this is angle theta is equal to 30 degrees in its size, and this is also angle theta is equal to 30 degrees in its size. In the next step, we will focus on the green right triangle BOM. So I'll copy the green right triangle BOM in a new page. So really, this is the green right triangle BOM that I copied from the original drawing. From the drawing it is very easy to see the tangents 30 degrees equals to OM over BM. Okay, tangents 30 degrees equals to OM over BM. OM is R, is the radius of the circle, so it is OM over BM. So here tangents 30 degrees equals to R over BM. We will multiply this equation by BM and then we divide it by tangents 30 degrees and we'll get that BM equals to R over tangents 30 degrees. Okay. So I actually found out that this side BM equals to R over tangents 30 degrees. In the next step, we'll join points O and C together by a straight line. And we will prove that the orange triangle OMC is congruent to the pink triangle OEC. Read again, we prove that the orange triangle is congruent to the pink triangle. So I write it down. The orange triangle is triangle OMC. We prove that it is congruent to the pink triangle, triangle OEC. Repeat again. We prove the orange triangle OMC is congruent to the pink triangle, triangle OEC. So, why those two triangles congruent to each other? First of all, MC equals to EC. Here, MC equals to EC, according to rule number 2. MC equals to EC according to rule number 2, or CM equals to CE. CM equals to CE. CM in the orange triangle equals to CE in the pink triangle. CM equals to CE according to rule number 2. Repeat again. Side CM in the orange triangle equals to side CE in the pink triangle according to rule number 2. In addition, side OM and side OE, they are both the radii of this circle, therefore they are equal to each other. So OM equals to OE. They are both the radii of the circle, therefore they are equal to each other. And finally, side OC is the common side that belongs to both triangles, so we can write down that OC equals to itself as a common side that belongs to both triangles. So we actually proved that the orange triangle, triangle OMC, is congruent to the pink triangle, triangle OEC, according to side rule. All the sides of the orange triangle OMC are correspondingly congruent to all the sides of the pink triangle, triangle OEC. So the pink triangle, triangle OMC is congruent to the pink triangle, triangle OEC, according to side rule. And from the fact that the orange triangle is congruent to the pink triangle, we derive that those two angles, they are equal to each other. So this is angle MCO in the orange triangle, and it is equal to this angle, this is actually angle OCE in the pink triangle. Angle MCO in the orange triangle equals to angle OCE in the pink triangle, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore those two corresponding angles must be also equal to each other. So if we define one of those angles as alpha, then the other angle must be also equal to alpha because they are equal to each other. Okay? So alpha plus alpha must be equal to 75 degrees according to what is given us in the question. That is to say 2 alpha equals to 75 degrees. We will divide this equation by 2 and finally get that alpha equals to 37.5 degrees. So this is angle alpha that is equal to 37.5 degrees, and this is also angle alpha that is equal to 37.5 degrees. In the next step, I will copy the right triangle OMC and we will analyze this right orange triangle, triangle OMC. Actually, this is the orange triangle, triangle OMC that I copied from the original drawing. OM is the radius of the circle, therefore it is equals to R. And this is angle alpha is equals to 37.5 degrees. In the right triangle OMC, tangents 37.5 degrees equals to OM over MC. OM over MC. OM is R, it is the radius of the circle, over MC. So in conclusion, found out that tangents 37.5 degrees equals to R over MC. It again, we found out that tangents 37.5 degrees equals to R over MC. Here we multiply this equation by MC and then we divide it by tangents 37.5 degrees, and we will get that MC equals to R over tangents 37.5 degrees. So actually found out that the length of this side MC is equals to R over tangents 37.5 degrees. So here BC equals to BM plus MC. So write it down. BC equals to BM plus MC. Side BC equals to line segment BM plus MC. It is very easy to see it from the drawing. BC equals to BM plus MC. BC, I'll repeat again, from the drawing it is very easy to see that BC equals to BM plus MC. BC equals to 2 units according to what is given as the question. So BC is 2 and it equals to BM. With that, right now found out that BM equals to R over tangents 30 degrees. So we substitute BM by R over tangents 30 degrees plus MC. We just right now found out that MC equals to R over tangents 37.5 degrees. So we substitute MC by R over tangents 37.5 degrees. So in conclusion, found out that 2 equals to R over tangents 30 degrees plus R over tangents 37.5 degrees. So 2 equals to, here we take R as a common factor out of those two expressions. And get the 2 equals to R was taken as a common factor. So what is left from R over tangents 30 degrees after we took from it R as a common factor? What is left is actually R over tangents 30 degrees plus what is left from R over tangents 37.5 degrees after we took from it R as a common factor. What is left is actually R over tangents 37.5 degrees. So actually found out that 2 equals to R and 1 over tangents 30 degrees equals to 1.732 plus 1 over tangents 37.5 degrees equals to 1.3032. So 2 equals to R and 1.732 plus 1.3032 equals to 3.0352. We divide this equation by 3.0352 and we get that R equals to 2 over 30352 equals to 0.6589 units. So I found out that the radius of this circle that is described by triangle ABC, the radius R equals to 0.6589 units. So in the next step, I will summarize the lecture. We start with the first method, of course. In this lecture, we found out the radius of this circle that is inscribed by this triangle, triangle ABC. We know that angle ABC equals to 60 degrees in its size, angle ACB equals to 75 degrees. In addition, we know that side BC of triangle ABC equals to 2 units in its length. Again, our mission is to find out the radius of this circle that is actually inscribed by triangle ABC. Or triangle ABC is blocked to this circle. So we have to find out the radius of this circle. Okay, in order to find out the radius of this circle, in the first method we actually did a construction, that is to say from point C we draw perpendicular on AB. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB as D. Then we focused on the right triangle, triangle DBC. So I copied the right triangle, triangle DBC in a new page and we analyze this triangle, triangle DBC. Actually, this is the right triangle DBC that I copied from the original drawing. Again, this angle equals to 90 degrees according to our construction. This angle equals to 60 degrees according to what is given as the question, and BC equals to 2 units according to what is given as the question. So in this right triangle DBC, cosine 60 degrees equals to BD over BC, or DB over BC. So cosine 60 degrees equals to dB over BC, and BC is 2. Cosine 60 degrees is 1/2, so 1/2 equals to BD over 2. We multiply this equation by 2 and finally found out that BD equals to 1 unit. Here, this line segment BD equals to 1 unit in its length. We continue to focus on the right triangle BDC and right triangle BDC. Sinus 60 degrees equals to DC over BC. Again, sinus 60 degrees equals to DC over BC. So it is DC over BC. BC is 2. So it is sinus 60 degrees equals to DC over 2. Because BC is 2. Sinus 60 degrees is square root of 3 over 2. So square root of 3 over 2 equals to DC over 2. We multiply this equation by 2 and finally found out that DC equals to square root of 3 units in its length. Here, this side DC equals to square root of 3 units in its length. Then we have in the right triangle DBC, this angle equals to 90 degrees, this angle equals to 60 degrees, 90 degrees plus 60, 90 degrees plus 60 degrees, it is 150 degrees. And therefore the missing angle here must be equal to 30 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So angle DCB equals to 30 degrees. Angle ACB equals to 75 degrees. So 75 degrees minus 30 degrees must be equal to the missing angle, angle ACD. 75 degrees minus 30 degrees, it is 45 degrees. Therefore the missing angle here, angle ACD equals to 45 degrees in its size. Then I copied the right triangle ACD in a new page and analyze this right triangle, triangle ACD. This is the right triangle, triangle ADC that I copied from the original drawing. We just right now found that angle ACD equals to 45 degrees in its size. So in the right triangle ACD, this angle equals to 45 degrees, this angle equals to 90 degrees. 45 degrees plus 90 degrees, it is 135 degrees. Therefore, the missing angle here must be equal to 45 degrees in size. In order to complete the sum of the angles in this triangle to 180 degrees, the missing angle here must be equal to 45 degrees. So we actually found out that triangle ADC, it is not only a right triangle, but it is also an isosceles triangle. Why? Because those two angles are equal to each other. And we have the rule that in front of equal angles in the triangle, they are equal sides. So in front of those two equal angles, we have those two sides that must be also equal to each other. But we know that DC equals to the square root of 3 units, therefore AD must be also equal to the square root of 3 units in its length. Here, AD must be equal to the square root of 3 units in its length, according to the rule that I mentioned. Okay, then I presented to you a new rule that is actually rule number, but before that, we continue to focus on the right triangle, triangle ADC. On the right triangle, triangle ADC, we implemented the Pythagoras theorem on this right and the isosceles triangle, triangle ADC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AD square plus DC square. Again, AC square equals to AD square plus AD square plus DC square. So AC square, that is the square of the hypotenuse, equals to AD square. AD is equal to 3, therefore AD square is equal to 3 square, that is 3, plus DC square. DC is equal to 3, therefore DC square is equal to 3 square, that is 3. So in total, AD square equals to 3 plus 3, that is 6. AC square equals to 6. We took a root out of this equation and finally found out that AC equals to the square root of 6 units in its length. AC, side AC of triangle ABC equals to the square root of 6 units in its length. So note that AC equals to the square root of 6 units in its length. Side AB equals to the square root of 3 plus 1 units in its length. And it is given as the equation that BC equals to 2 units in its length. In the next step, I presented to you rule number 15 and implemented rule number 15 in our drawing. According to rule number 13, the radius of a circle that is inscribed by triangle ABC, the radius R equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the triangle. So here we have, this is triangle ABC that could be any triangle, and this triangle ABC blocks this circle, or the circle is inscribed by triangle ABC. So actually, according to rule number 15, we can know what is the radius of this circle that is inscribed by triangle ABC only by knowing the sides of the triangle, only by knowing the area of triangle ABC and the sides of triangle ABC. Again, the radius of this circle that is described by triangle ABC, the radius R equals to the area of triangle ABC that blocks the circle over the semi-perimeter of this triangle ABC. And the semi-perimeter of triangle ABC equals to the perimeter, that is actually AB plus BC plus AC over 2. Okay, we can actually implement rule number 15 in our drawing. Why? Because in our drawing we know all the three sides of triangle ABC, and because of the fact that we know all the three sides of this triangle ABC, we can calculate the semi-perimeter, and it is very easy also to calculate the area of this triangle. The area of one triangle equals to the base of the triangle times the height to the base over 2. So, according to rule number 15, the radius that we are looking for, the radius R of this circle that is described by triangle ABC, will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of this triangle ABC. Again, the radius of the circle that is blocked by triangle ABC equals to the area of triangle ABC that blocks the circle over the semi-perimeter of triangle ABC. The area of triangle ABC equals to the base of the triangle that is AB times the height to the base that is DC over 2. Again, the area of triangle ABC equals to the base of the triangle that is AB times the height to the base that is DC over 2 over the semi-perimeter of the triangle ABC. The semi-perimeter of triangle ABC equals to the perimeter that is AB plus BC plus AC over 2. Again, the semi-perimeter S of triangle ABC equals to AB plus BC over 2. Here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. And finally we get that the radius of the circle that is inscribed by triangle ABC equals to AB times BC over AB plus BC plus AC. AB equals to the square root of 3 plus 1 units in its length. AB equals to the square root of 3 plus 1 units in its length times DC. DC equals to the square root of 3 units. So it is square root of 3 plus 1, that is AB, times square root of 3, that is DC, divided by AB, that is square root of 3 plus 1, plus BC, that is 2, plus AC, that is square root of 6 units. AC equals to the square root of 6 units. So the radius of the circle that is described by triangle ABC equals to the square root of 3 plus 1 times square root of 3 over square root of 3 plus 1 plus 2 plus square root of 6. The area of triangle ABC equals to 2.366 square units over the semi-perimeter. The semi-perimeter of triangle ABC equals to 3.591 units, and 2.366 over 3.91 equals to 0.6589 units. So actually found out that the radius of this circle that is inscribed by triangle ABC equals to 0.6589 units. Okay, so we finished with the first method. Then I presented to you how to find out the radius of this circle that is described by triangle ABC. According to the second method, we define the center of this circle as O. We define the point of tendency of tangent BC with this circle as M. We define the point of tendency of tangent AB with this circle as D. We define the point of tendency of tangent AC with this circle as E. We join points O and M together by straight line. OM is the radius of the circle. The radius of the circle is drawn to point M, that is the point of tendency of tangent BC with this circle, and whenever radius that is drawn to the point of tendency, then this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. Again, this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. According to rule number 1, also this angle equals to 90 degrees, and this angle equals to 90 degrees. Then we focused on the common extent point C. From the common extent point C, we have two tangents to this circle, tangent CE and tangent CM. And according to rule number 2, they are equal to each other. That is to say, CE equals to CM. Here, CE equals to CM according to rule number 2. Likewise, we focus on the common extent point B. From the common extent point B, we have two tangents to this circle, tangent BM and tangent BD. And according to rule number 2, they are equal to each other. That is to say, BM equals to BD, or BD equals to BM, according to rule number 2. Then we join points O and B together by straight line, and join points O and C together by straight line. By joining points O and B, we can get here those two triangles, the yellow right triangle and the green right triangle. And we proved that those two right triangles can go into each other according to side rule. Why those two right triangles can go into each other? First of all, those two sides are both the radii of the circle, therefore they are equal to each other. BD equals to BM according to rule number 2. BD equals to BM according to rule number 2. And BO is a common side that belongs to both triangles, so I can write down that BO equals to itself. So those two triangles can go into each other according to side rule. All the three sides of the yellow triangle are correspondingly equal to all the three sides of the green triangle BOM. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if one angle is theta, then the other angle must be also equal to theta because they are equal to each other. So theta plus theta equals to 60 degrees. Here, theta plus theta equals to 60 degrees, that is to say 2 theta equals to 60 degrees. We divided this equation by 2 and finally found out that theta equals to 30 degrees. This angle theta equals to 30 degrees in its size. Then we focus on the green right triangle BOM. So I copy the green right triangle BOM in a new page. This is the green right triangle BOM that I copied from the original drawing. OM is the radius of the circle that is equal to R. This right triangle BOM tangents 30 degrees equals to OM over BM. Okay, OM is R, so it is R over BM. Here we multiplied this equation by BM, and then we divided by tangents 30 degrees and found out that tangents 30 degrees, that BM equals to R over tangents 30 degrees. Okay, here, this side BM equals to R over tangents 30 degrees. We repeat it on the same process on those two right triangles, the orange triangle and the pink triangle. Repeat again. The orange triangle OMC is congruent to the pink triangle OEC according to side rule. Why? Those two sides are both the radii of the circle, therefore they are equal to each other. CE equals to CM according to rule number 2. Again, CE equals to CM according to rule number 2. And OC is the common side that belongs to both triangles, so OC equals to itself. So all the three sides of the orange triangle OMC are correspondingly equal to all the three sides of the pink triangle OEC. Therefore, those two triangles can go into each other according to side rule, and from the fact that those two right triangles can go into each other, we derive that those two angles also are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if this angle is alpha, then their angle must be also equal to alpha because they are equal to each other. That is to say, alpha plus alpha equals to 75 degrees. So 2 alpha equals to 75 degrees. We divided the equation by 2 and finally found out that alpha equals to 37.5 degrees. This is again alpha that is equal to 37.5 degrees. Then I copied the orange triangle OMC in a new page and we analyze this orange triangle OMC. This is the right triangle OMC in the orbit from the original domain. This angle equals to 37.5 degrees. It is angle alpha. OM is the radius of the circle that is equal to R. So in the right triangle OMC, tangents 37.5 degrees equals to OM over MC. OM is R, so it is R over MC. Then we multiply this equation by MC, and then we divide it by tangents 37.5 degrees, and found out that, again, tangents 37.5 degrees equals to R over MC. Repeat again, we multiply this equation by MC, and then we divide it by tangents 37.5 degrees, and found out that MC equals to R over tangents 37.5 degrees. If this side MC equals to R over tangents 35 degrees. Okay, so BC in total equals to BM plus MC. Again, BC equals to BM plus MC. BC is 2 according to what is given as the equation. BC is 2. BM is tangents R over tangents 30 degrees. BM is R over tangents 30 degrees. And MC is R over tangents 37.5 degrees. Again, MC is R over tangents 37.5 degrees. So we found out that 2 equals to R over tangents 30 degrees plus R over tangents 37.5 degrees. Here we took R as a second factor from those two expressions and found out that 2 equals to R, so R was taken as a second factor, so inside the brackets we left only with 1 over tangents 30 degrees plus 1 over tangents 37.5 degrees. So 2 equals to R, and 1 over tangents 30 degrees is 1.732, and 1 over tangents 37.5 degrees is 1.3032. So 2 equals to R, and 1.732 plus 1.3032 equals to 3.0352. So 2 equals to R times 3.0352. We divided this equation by 3.0352 and finally found out that the radius R of this circle equals to 0.6589 units. So in both methods we found out that the radius of this circle R equals to 0.6589 units. Okay, thank you very much.